So in this session, we're going to start with the mathematics behind machine learning and deep learning. So mathematics required to understand AI, ML, and DL. The first thing that we're going to start is linear algebra. So the linear algebra, it's a branch of mathematics which basically focuses on vector spaces. Again, to reiterate that, I do not want you to, and I do not expect basically you to know what vector spaces are, but just keep this in mind that we have to deal with something called as vector spaces. So the applications of this algebra, it's a broad subject, and the applications sort of hover over physics. Then we have other engineering domains, computer science, in which we have machine learning, deep learning, and other things. Let's to understand this, I'll take a different approach because how this algebra is being taught in schools, and it really is not intuitive, and sometimes we feel that why are we studying this. And to do that, I'll just start with the bare bone basics so that you understand what is going on with this. So the thing I'll start with is basically a point. What do I understand by a point? So before going into the deep, what is a point and what is a vector, what is a matrix, I want everybody to be on the same page. We'll define what is called as coordinate system. Coordinate system. As I said that mathematics basically is a language. So anything that exists in the physical world, we try to capture it in numbers, or we try to capture it in somehow so that it can be communicated to other people, and maybe we can sort of extend these things so that have a deeper understanding of these things. Let's suppose we want to define position of somebody. So position, it is a relative concept. For that, we have to define what's called as frame of reference. So if I say like some people are in this session are from Bangalore, some people are from Kashmir, and in the Kashmir they are from different parts. So how to measure these things basically? So for that we must have a system which we'll use as a reference, and from that we can sort of measure the things. So there are a lot of coordinate systems, but the main coordinate system that we'll focus on is called as Cartesian coordinate system. Cartesian, or some people pronounce it Cartesian coordinate system. So what I mean by that is, suppose a point is here in the space. What if I want to measure it, and I want to measure what is the position? So what I'll do is I'll create a coordinate like this. So this is one line and this is the other line. So I'll call this point as origin. I'll say this point is origin. Origin basically means 0 0. So if something is here, so it is at the origin, and the system that we have here is 0 0. So we created two axes. One is x axis and the other is y axis. Okay. Now in order to go to this point, so what should I do is I should take some steps in this direction. I should take some steps in this direction first. Okay, then I should take some steps in this direction to reach this point. The number of steps, or the unit of steps that I walked in this direction, is called its x coordinate. Let's call it x1. Okay, then the number of steps, the units I sort of walked in this direction, is called as y1. Okay, so every point in a 2D, so this is called as 2D Cartesian coordinate, because I have two axes over here. I have an x-axis and I have y-axis. So what I mean by that is, if I have to identify any point in that 2D coordinate system, so I have to specify what is its x coordinate and what's its y coordinate. So I call these points as coordinates. Coordinates. Okay, so this is the basic concept of the Cartesian coordinate system. So we have different coordinate systems, but the majority of the times we'll be using this Cartesian coordinate system. We have something called as polar coordinates, then we have cylindrical coordinates, spherical coordinates. This is the first thing that I want you to get concrete in your head, so that then we can move forward with the different definitions. So what is the Cartesian plane then? So this is called a Cartesian plane. So this is called a Cartesian plane. So whatever I made here is called a Cartesian plane. So what are the properties that this Cartesian plane have? The first thing is it has an axis, x-axis, and it has another axis as y-axis, and they are perpendicular to each other, that they form a 90-degree angle. So this angle is 90 degree. So they form this 90-degree angle, and it divides sort of things into four quadrants. If I again make it like this, okay, so this is our x-axis here, and this is our y-axis. So here I call this point as origin. So this is our origin. Okay, then here we have positive values 1, 2, 3, 4, and so on. So here we have negative values -1, -2, -3, -4, and so on. In the similar fashion, in this y-axis, we have +1, +2, +3, and so on. So here we have -1, -2, -3, and so on. So if you see, this is first quadrant, this is the second quadrant, and here this is the third quadrant, and this is the fourth quadrant. So now if I position any point, and then I can sort of give you the position of that point. Suppose I have a point, let's put a point over here. So if anybody wants me to tell, so where is this point located? So what I'll do is, I'll just draw a perpendicular here and draw a perpendicular here. So the first coordinate x-axis, it's -4. So I'll write this point is as -4, its x coordinate, and maybe y coordinate is, let's suppose, 5. So this is 4 and this is 5. So y coordinate is 5. So this point P, it is written as -4, 5. Is the concept of coordinate system Cartesian plane clear?
Yes, sir.
Okay. So in order to show you that in the code, I'll first switch to the coding window to show you those things, so that these things are concrete in your head. So here in the code, what I have done is, I have plotted a figure. I have a point whose x coordinate is 3. Then I have the same point whose y coordinate is 4. Then what I am doing is, I am plotting a figure and plotting basically a point onto that coordinate system. If you just see it here, you can see there is a point which has 3, 4 as its uh, coordinates. X coordinate is 3 and y coordinate is 4. So this is the x-axis, and we have the y-axis as well. So here this point is as origin, where my arrow is right now. So it is the origin, so it is the 0, 0 value. So this is the first thing I want you to get into your head, so that it becomes clear for you, what do I mean by coordinate system, what is the point. Then I can move with the algebra part itself. Okay, now if I want to sort of extend this, so here we have what is called as 1D point. So 1D point, it's also called as scalar. So if we describe something by just one axis, suppose as we had this axis, we had an x-axis and we had an y-axis. Let's suppose this is the origin. If there is a point which either lies on this axis or lies on this axis, so here the x coordinates, let's suppose x1, and its y coordinate is 0. Okay, here the x coordinate is 0 and y coordinate, let's suppose it's y1. So these 2 points, or the points which lie on this line, or the points which lie on this line, I mean the points which lie on x-axis or the y-axis, they can be described by just one value. So in this case, if it's lying on x-axis, so we can just say x1 or x1, x2, x3, something like that. So if it lies on y-axis, then we can just have y1 or things like that. So these are called as scalars, because these points, we only need one thing to describe them, just a value. Okay. Now let's go to the 2D points. We call them 2D points. 2D points, or they are called as vectors. Okay, so here whatever we discussed so far was actually a 2D point. So 2D points look like this. So we have an x-axis and a y-axis. So if a point is there right here, so it has some x coordinate. Here it's x1, so value will be x1, and it has a y coordinate as well. So here this is y1. If a point is if described by having two coordinates, x1 and y1, so we call it a vector. And even it can be more than one coordinates, then it can be 2D points or vectors, or we can say they can be ND points as well. Okay, so they are called vectors. So now we can write in a succinct way like this. So we can write x1 over here and y1 over here. So this is what I mean by a vector. Okay, then I can have the similar, in the similar fashion, I can have 3D Cartesian plane or 3D coordinate system. So in that I'll have three axes. So one will be x-axis, and we'll have y-axis and the z-axis. This is x-axis, and this is y-axis, and this is z-axis. So if there is a point onto this plane, onto this coordinate system, suppose I have a point here, so I'll draw perpendicular on the x-axis. Let's suppose this is x1. So I'll draw a point onto the y-axis. Let's suppose this is y1. Then I'll again drop a perpendicular to the z-axis as well. Okay, This coordinate system basically is like this. So if you see it like this, we have an x and a y and a z, if it is visible on the screen, because my camera is too bright because of the lights I have. So I have z1 coordinate as well. So now I describe the things in 3D: x1, y1, and z1. So this I can call it a 3D Cartesian plane, or 3D plane, 3D Cartesian plane. This is how I describe the points in 3D. So after 3D, we cannot imagine in 4D, 5D, and ND. So that's why we use the concept of linear algebra, because now we can describe the 2D vector like this, and we can describe 3D vector like this: x1, y1, and z1. Okay, so this basically is a 3D vector. Okay, then in a similar fashion, if I have to write 4D vectors, now I cannot visualize the 4D thing. I can, my eyes are constrained, sort of our eyes are constrained, so that we can just visualize 1D, 2D, and 3D. But for that, linear algebra is tool. That's the beauty of maths. You can basically capture the things which you cannot imagine even. So if we write a vector, let's suppose v, that's equal to x1, x2, x3, and x4. So here we have a point which lies in 4D space, but we cannot imagine 4D space. And for that sake of matter, so we can have a vector which can have x1, x2 up till xn. This lies in ND space. Okay, so this lies in ND space, and here it lies in 4D space. But as our brains and eyes are constrained, so we can just look visualize till 3D. So I also like to show you a point that we can plot in 3D. So matplotlib gives us a 3D graph as well. So if I show you it in the code, so here you can see that. So again, the similar thing, I am defining three coordinates: x coordinate, my y coordinate, and the z coordinate. Then I'm plotting the figure, and I'm using what's called a scatter plot. So I'm plotting x, y, and z. So if I plot this point, so clearly you can see there is a red point. Here we have x coordinate. This is nearly equal to here, this value, and then we put a perpendicular on the y-axis. That's here, and the perpendicular is on the axis. That's the value we gave here. So 3, 4, and 2. This is the point that described in the 3D plane, if you see it. So we have these 3D three coordinate systems. Beyond that, we cannot imagine. That's why this vector concept of the algebra comes into play. Is the concept of point and these Cartesian coordinates clear? Is it clear?
Yes, sir.
Nice. Now I'll go into some details of what a vector means. So I'll go into the details of what is a vector basically. So what a vector means. So if you see, there are three perspectives to see this vector. So one is the physics student's perspective, how physics people see it, and one is the computer science perspective, and the other is mathematician's perspective. So these people use these terms in some other way. For example, if you ask a physics student what is a vector, so what he'll do is he'll say a vector is a quantity which basically has a magnitude and a direction. Okay, so they will say anything that has magnitude as a direction is called as a vector. They usually denote vectors as v, and they'll say if it is a direction, let's suppose they'll plot a vector like this. They'll say this is a vector because it has a magnitude. This is the magnitude of the vector, and it's a particular direction. So this is from physics perspective. It has a magnitude and direction. So if you ask a CS student what is a vector, so he'll just make a bunch of numbers. He'll say 1, 2, 3, 4, and this is a vector for him. So mathematician, what they do is they combine both of these concepts together. So they combine both of these concepts to generalize the vector. So they make what is called as a vector space. So they say any element that belongs to this vector space is called a vector. So this may look abstract way to do, because mathematicians, they first define the things abstractly, then after they have real world applications. But if you ask a physics student, he'll directly say a vector has a magnitude and a direction. So that you might have seen velocity, for example, displacement. They say the person is running with this velocity in this direction. So it means it has a magnitude as well as a direction. So CS students or CS folks will just represent vector by the numbers. So we have this 1, 2, 3, 4. It's a vector. It has a bunch of numbers in it. So mathematicians, they say, so there is something called as a vector space. It has formal definitions. This vector space is a formal definition that I want to go into, because we are not here discussing the mathematical aspects of these things. We just want to see the applications. And then they say any element that belongs to this vector space is actually a vector. Okay, so that's what they mean by this vector. So now we'll mostly use physics students perspective and CS students perspective. For physics, we'll understand what I mean by the vector, as we just plotted many of the graphs through these points. So any of this point can be represented by a vector. Suppose we had this vector, let's suppose this point. So here I can just draw a line like this. So this basically is a vector representing that point. So this is a vector. If I just draw some other Cartesian plane like this, if I describe a point here, so if I have a line from the origin to here, so this is a vector, because now this represents magnitude and it also represents direction. So here, if it is the values x comma x1 comma y1, so we can represent the vector like x1 y1 like this. Okay, so this is the magnitude. We generally suppose this is vector x. So magnitude of vector x is written like this. Sometimes it's written like modulus of x, or sometimes they put double mod over this to show that we are talking about the magnitude. If you write x and then put a little arrow onto this, this shows that this is the vector we are talking about. Okay, suppose I want to make these vectors on the code. So how to do that? So we'll go on to the coding screen to show you that. So there is something called a square, a function which there is in matplotlib. So I have these 2 points. V1, it's a vector. It has a value 2 comma 3. It basically is a point in that lying in the 2D plane. Then I have a vector v2 minus 1 comma 4. Let's suppose I want to plot these vectors how a physics student perspective will look like. So I'll just run the cell. You can see that there are two vectors. So basically this is vector v2 in the red and vector v1 it's in the blue. It's shown in here. So I hope that at least the concept of vectors is clear, how we represent them in the space, and then what I mean by a point, what I mean by a Cartesian plane. All of these concepts are clear so far. Can I move ahead?
Yes, sir.
Okay. Let's move ahead with the real concepts now. We'll see some things. Let's suppose we want to find a distance. Now the topic that we'll have is distance of a vector, or we can call it a point now, because you know that a vector basically is a point. Distance of a vector or a point from origin. As you saw, everything is measured from the origin usually. So this is the origin. If you want to see the distance, so as I said, vector is having the magnitude, and I want to see the distance or the magnitude. If I want to measure the magnitude, or I want to measure the distance of a vector or a point from the origin, so how to do that? As you know that vectors can be of many types. The first, we can have 1D vectors, we can have 2D vectors. Basically we can have a point which is just x1, then we can have x1 x2, or we can have suppose 3D points x1 x2 and x3, or we can have nd points x1 x2 up till xn. Okay, so if we want to measure the distance from the origin, so what will be that distance? Let's suppose deal with the first case of 1D case. Let's deal this in 1D case. Let's suppose this is a Cartesian plane. Okay, and this is the origin 0 comma 0. As I told you that any point that lies on either x-axis or y-axis, that is a 1D point. Let's suppose I have a point over here. Okay, so how to measure the distance of this point? Directly, what are the value here is of x1? That is the value, that is the magnitude. So we can write, if this vector is x, so I can write magnitude of x is basically x1 directly. So, or we can say x1 minus 0, because it starts with 0. So x1 minus 0 is basically x1. So that's how we measure the distance of a 1D point. It's not so interesting. So now what'll I do is, I'll go with the 2D distances. If I have a 2D vector, how to do that? So again, I'll have, let's make a good Cartesian plane. So here, this is the Cartesian plane, and here we have the origin as 0 comma 0. Let's suppose I have a point in here. This is a point P, and its value is x1 comma y1. So by magnitude, I mean that I have to measure this distance. That's the distance. This is the vector that we are representing. I have to measure this distance. So this is our vector, let's suppose x. I have to measure this. So how to measure this? So if you know Pythagoras theorem, so what I'll do is I'll just put a perpendicular here. So this distance x square, I can write it. Let's call this a and let's call this b. Okay, so I can write a square plus b square. So but I know what is the value of a, because here the value of a is x1, because this is x1 distance on the x-axis. So I can write this x square is equal x1 square plus this is basically the distance y1. So because if I drop a perpendicular here, this is what I mean by distance. This is y1, and here this is x1. So I can write x1 square plus y1 square. So now if I need to find the magnitude x, so I'll write it like this. This is equal to under root of x1 square plus y1 square. So in the similar fashion, we could have done the similar thing here. So we found a pattern. So if we see the 1D point, 1D point's this magnitude distance is basically equal to x1 square root. But you know that root and square gets cancelled, this is also equal to x1. That's why I read directly is equal to x1. For the 2D, if you see, I applied Pythagoras theorem to show you that this x square, this distance is equal to x1 square and y1 square. So here then I applied under root, so this is the distance basically. So this is distance of a 2D point from origin. Origin basically is 0 comma 0, and this is origin. Again, if I want it to extend to 3D, okay, so how 3D axis will look like? I have an x-axis, I have y-axis, and I have z-axis. So if suppose there is a point here, let's suppose p is equal to x1 comma x2 comma x1 comma y1 comma z1, let's suppose. So in the similar fashion, I can prove that the distance of this point, let's suppose this is the vector that we have, its distance, let's suppose, is d. So again, now the magnitude of this d vector is basically equal to square root of x1 square plus y1 square plus z1 square. Okay, so this is for the 3D vector or the 3D point. So this is for the 3D vector. So we can extend the idea to the nd vector. So if I have an n dimension which I cannot imagine, suppose I have an nd vector which I cannot imagine. So similarly, I can do that. I can say the distance of that nd vector from the origin is basically square root of howsoever many components that have. Let's suppose we have x1 component x1 square plus x2 square plus x3 square plus and so on till xn square. So I can write this in the succinct way. I can write it like square root of summation of xi square I is equal to 1 to n. So this is the distance for an nd vector or for a nd point. Let's take an example. If I have a point which measures, let's suppose here it has the measurement of 2 comma 3 comma 4, and I want to see what is the basically the magnitude of it. Now I know that the magnitude d is equal to under root of 3 square plus 4 square. This is equal to 9 square plus 16. 9 plus 16, that's basically equal to root of 25. So that's equal to 5. So magnitude of this vector is 5, if you see it that way. So if I give you any vector, let's suppose now I give you a vector from a computer science perspective. I am having a vector, let's suppose x. It has the values 4, 1, 2, 6, 3, 2. Can anyone among you give me the magnitude of this x? So what should be the magnitude of this x and how to calculate it? I'll just pause here for maybe few seconds so that you calculate it. Okay, anyone with the answer? I don't want to give the exact answer. Can somebody just speak? So how to calculate it basically? I'll read the expression, whatever you say. Maybe Rian, if you are there, can
Square every number and add them and then finally make a root.
yes. So this is the basically what I mean by distance from the origin. I hope that this concept is clear. Let's now go to the coding window, and I want you to show if you want to find these things in the code how to do that. We'll give example of like, let's suppose 2D and 3D points so that you understand it better. So let's suppose this is the 1D vector that I want to find the value of. So this point origin is 0 basically, and the point has just one coordinate 5. So as you know that its magnitude basically is directly 5, and you can visualize it as well. So here you have, this is the point, and I have just used this arrow. So this is the magnitude of this. This is the origin 0 red point, and in here we have this blue point, and the value is 5 directly. Now let's suppose we have a 2D point. We have the origin as 0 comma 0. I have defined an origin here 0 comma 0. Then I have a point 3 comma 4. Now I need to calculate distance. As you know that this is something called as norm as well. So square root of the squares of numbers is also called as norm. So what I wrote is I wrote point minus origin, the norm of that point. So this gives me the distance. Now I can compute the distance in other code here. It just gives me the distance of these points. So here this is the origin, and this is the blue is the point that I want. And you saw that the 5 is basically the magnitude of this vector. or the distance of this blue point from the origin. And similarly, I can do it in the 3D. So I have origin 0 comma 0 comma 0 because it has three components, and now a vector which has also three components, 2 comma 3 comma 1. So again I can use the function norm, but if you want to calculate it, you can also write the formula as 2 square plus 3 square plus 1 square under root. So that will be the distance, and now I want to plot it. So if I want to plot it, so this is how it will look like. So this is the distance, and I can also plot this distance. If I want to print the distance, so I can just print it, the distance, print the distance of this. So here the distance is 3.74 from the origin, and this is how it looks like in the 3D. Now from 3D onwards we cannot imagine, but still algebra gives us the tools so that we can compute these values irrespective whether we can imagine or not, but still we have the ability by algebra so that we can sort of compute these values without even imagining. Is that clear? So I've also given the whole things in just one graph. So this is the 2D vector, and the distance from the origin in 1D is 5, and from 2D is also 5, from 3D is 3.7. So this is the vector in 3D. Is it clear? Nice. So now what I'll go is I'll find the distance within the 2 points. Now I saw how to find the distance from the origin. Now if I want to find the distance between 2 points, so the other topic that we'll be studying is distance between 2 points. Now you know that the first 1D case is like it's so simpler. 1D case is usually simpler, so we'll start with the 2D case. But 1D case basically directly means that if we have a point in 1D, if I have a point, let's suppose x1, and other point is x2. So if I want to find a distance, I'll just subtract these points, x2 minus x1. So if I want to find the distance. So this is for the 1D case. But it becomes interesting when we go into the 2D case. So let's suppose again we have a Cartesian plane like this. So here we have an origin, and we have a point here, and we have a point here. So I can draw vectors like this. This is one vector, and this is the other vector. Okay, let's suppose this point is P, its value is x1 comma x2. Let's suppose. And then we have another point y1 comma y2, let's suppose. So we have, let's suppose we'll give it x1 comma y1 so that it becomes, calculation becomes easy. And now we have another point here P, it's x2 comma y2. Okay, basically what we want is we want to find this distance. This is the distance that I want to find. Okay, so what is the formulation in this 2D? And it's really easy to prove. The thing is basically if I want to compute the distance, let's call this distance as d. Okay, so this d basically is equal to x2 minus x1. Okay, so first I'll subtract them and square them again, and then plus y2 minus y1, I'll square them and put in under root. Again I can use the Pythagoras theorem to prove it. So let's take this proof as an exercise. This is a simple proof. You can just use the Pythagoras theorem to find the distance, and then you'll end up with this formula. So this is the formula basically which we will use in 2D case if I want to compute the distance between these 2 points. This basically was x2. So in order to reach here, so what I did is, so these are the coordinates. So I'll just subtract these coordinates pairwise. I'll do the subtraction, x2 minus x1, and then basically I'm squaring it up. It doesn't matter if I to do x square minus x1 or x1 minus x2. It doesn't matter because I'm squaring the terms. Then I have this y1 minus y2 and whole square. Then I'm putting an under root for this. So this is how we compute the distance between the points in the 2D plane. Let's suppose we have this ND now. So again the similar thing. If I have a point, if I have points, let's suppose P, which has the coordinates, let's suppose x1 comma x2 comma x3 till xn. This is one point or one vector. Let's suppose we have another Q. So its values are y1 comma y2 comma y3 and so on till yn. So if I want to find the distance PQ, if I want to find the magnitude of this, if I want to find the distance of this PQ vector, so what will I do is I'll just put a square, and correspondingly I'll subtract these terms, x1 minus y1 whole square plus x2 minus y2 whole square till xn minus yn whole square. So in a succinct way I can write it like this: summation of xi minus yi, I goes from 1 to n whole square. This is how we'll compute the distance between the points. So if I have 2 points, I want to compute the distance. You might have seen this in the coordinate geometry as well. Okay, just seeing it in the coding window so that we find the distance. Let's go over to that. Now here, I think it's here. So I have written a function calculate the distance between point 1 and point 2. So then I'm again finding the norm between these point 1 and point 2. This is basically is finding the norm and it will return the distance and the dimensions of that point. So let's suppose in the 1D I have point 2 comma 7, in the 2D I have this 1 3 4 7. 3D points are 1 2 1 4 0 1. So these are the 3D points. And I'll compute the distance and plot these things if you see it here. So this is the distance between these 2 points, and then in the 3D this is the distance between these 2 points. So if you see it in here, so 1D I do not need to plot, so I directly showed it here. I hope that you understand these concepts, how to find distance, and I'm explaining the formulas and then using the same formulas in the code as well, and then showing the plots how to compute the distances. So why I'm showing you these many plots, but because when we'll be moving into the algebra by adding these vectors, then multiplying the matrices, that time you'll get the clarity of the concept. So this is what I mean by multiplication. Why do we do a multiplication in a certain way? And why should we just take one row then multiply it by the column and perform the dot product? So that really becomes important and it becomes interesting when you know all of this stuff, all of these concepts. So except if you do not know these concepts, this algebra becomes just some things which you just perform computations, but you do not have an intuition. Is the thing still now clear? Whatever I showed you till now, is it clear?
Yes, sir.
Nice. Now, whenever I call so vectors, if I say a vector, so there are two types of vectors. So I just want to clear this upfront so that there is no confusion. One is called as a row vector and is called a column vector. The very basic terminologies, but I want you to have do know this because I'll maybe sometimes use something and I'll assume that you know it, so that that time you must also know that, and do not make any assumptions which I haven't told you. So row vector is anything if I write, if there is only one row, it has number of columns x1 comma x2 and so on till xn. So this I call as a row vector. So what a column vector is, it just has a column. So in here you can write it has one row and let's suppose n columns. So this is called the dimension of the vector. So this vector is called a row vector. If its dimension, it has one row and n columns. This is called a row vector. What column vector is? It basically has one column and n rows. So here we can have x1, x2, and so on till xn. This is called a column vector in a sense. So whenever I say just a vector, assume that I am speaking about the column vector. When I am saying a vector, you should get this picture in your head. Then I am speaking about this column vector. As you know that there is a operation transpose, sometimes I'll write vector transpose. Now this is a row vector. So whenever I'm speaking about v, that is directly a column vector. So now you know that by transpose, what I do is I'll convert rows into columns. So if I spoke about v transpose, that is a row vector. If I speak about just v, that is a column vector. I wanted to get these terms so that I may not make any assumptions. So let's move ahead with the what is called as the product of vectors. All of these things will make sense, just bear with me, and all of these things will make sense in the code because these things are used a lot. So as you know that we have this vectors, let's suppose v1, and we have this vectors v2. So v1 can be 1 2 3, and let's suppose v2 is 2 4 6. Okay, I can write addition of these vectors, v1 plus v2. So what I mean by that is this is component word addition. You might have heard component word addition. Now each of this is a component of a vector. So what I mean by this v1 plus v2, it is basically the component wise addition. 1 plus 2 is 3, 2 plus 4 is 6, 3 plus 6 is 9. So I just added it the component wise. So this is the basic concept of addition of vectors. Addition of vectors. But we have multiplication of vectors as well. So multiplication, multiplication of vectors. So first we defined what a vector is, then we moved on the operation of vectors. What can be done with these vectors? So that we saw we can do addition, and the similar way we can do subtraction as well. So we can do subtraction as well. But the interesting case is multiplication of a vector. So there are two types of multiplications. One is called as vector dot product, and other is called as vector cross product. So this thing really becomes important for physics folks, this thing, and we won't be giving much of the details over here. So but we'll be dealing with vector dot product because this is what we'll be heavily using. So our focus will be this will be our focus, vector dot product. So I'll just explain the vector dot product, what these are, and then we can move ahead. So as you know, now we can represent a vector. Let's suppose a is a vector, and this vector has values a1, a2, and a3. This is a vector a. Then let's suppose we have vector b, and that is b1, b2, and b3. That's a vector b for us. If I want to perform multiplication, by multiplication I now mean the dot product. So what I can do is I can multiply them component wise and add them together. So what is a dot b? I'll write it like this: a dot b. So a dot b basically is equal to a1 multiplied by b1 plus a2 multiplied by b2 plus a3 multiplied by b3. So this is what I mean by the dot product of the vectors. So this is how I define that. If I know the two vectors, so I can define the dot product like this. This is by definition the meaning of dot product. So let's go to the geometrical interpretation. What do I mean by dot product? So uh, what are the things that I can sort of get from this dot product? So this is called as geometrical interpretation. So let's suppose we have these vectors. Let's just take two vectors. We have a vector a and we have a vector b. This is vector a and this is vector b. So if I know these components of these vectors, if I know component, I can just perform this. So by definition, you can also write this dot product as a dot b can be written as magnitude of a, magnitude of b cos theta. So because there, this is the angle theta in here. So if you know, this is the angle theta. So this is again the definition of dot product if you see it geometrically. Okay, so what is the meaning of this? So I can show you. This is the theta and we can compute the theta. By dot product you can get to know what is the angle between these two vectors. So if there are two vectors and you want to see how are they aligned in the coordinate system, so you can compute this by using the theta. If you want to just compute the theta, you can just write theta is equal to cosine inverse of a dot b divided by magnitude of a and magnitude of b. So this is how you can find the angle by using the dot product. So if you know the components a, if you know components b, and you can find the magnitude. If I know the components, let's suppose components are something, so I can do theta is equal to cosine inverse of what is a dot b. So basically a1 b1 plus a2 b2 plus and so on an bn. So this is the meaning of dot product and then divided by. So now what's the magnitude? As you saw, the magnitude is basically the distance from the origin. So I can just write under root of a1 square plus a2 square and so on an square multiplied by under root of b1 square plus b2 square plus and so on bn square. So this is how I can find the angle between the two vectors. And what this angle tells me, basically tells me the relation between these two vectors. There is a concept called as orthonormality. We'll see that, but just stick with me and sort of think about these concepts by using this geometrical interpretation. I can find the angle if I know the components of these a vector and b vector. So I sort of defined this a dot b as a, magnitude of b cos theta. Then I can find this cos theta like this, cosine inverse of a dot b divided by magnitude of a, magnitude of b. Then I can again expand it. Writing it in a succinct way, I can just write theta is equal to cosine inverse. Again, I'll write summation of ai bi. I goes from 1 to n divided by. I'll write square root of, okay, summation of ai 1 to n. This is square multiplied by again square root of summation of bi whole square I is equal to 1 to n. And this is how I can write in the succinct format. So I also explained you the what does the summation stand for. So this is basically just a succinct version. I just compress these things. So this is what I mean by the dot product of vectors and how I perform these dot product. In the NumPy we have the functions np dot, so where we can perform the dot product. But is this geometric interpretation clear? Is it clear?
Yes,
Yes,
sir.
sir.
Nice. There is a beautiful concept. What if there is this theta is equal to 90? Let's suppose theta is equal to 90. So what I can conclude from that is, so I'll perform a dot b, as I know that a dot b is magnitude of a, magnitude of b cos of 90 now, because theta I have assumed it's 90. So you now know that a dot b is equal, because cos 90 is 0. So this a dot b is 0. Whenever you find that the dot product between two vectors is 0, it is sure that these two vectors are perpendicular to each other. This is vector a and this is vector b. If the dot product between two vectors, let's suppose a is a1 b1 plus a2 b2 and so on, a and bn, let's suppose this is equal to 0, then for sure I can say that this angle is 90 degree. So the two vectors whose angle is 90 degree, they are called orthogonal vectors. Remember this. The two vectors, if the angle between these two vectors is 90 degree, we call them orthogonal vector. So let's again go to the coding window so that I can show you these things in the visual format. Now here I have plotted this is the first vector 3 comma 4, then I have vector 5 comma 2, then I perform the dot product because I told there's a function np dot. What it does, it'll basically take each component, multiply, and then add the components together. And again I'm saying magnitude of a. So magnitude of a, basically I'm just finding the norm of a, square root of a1 square plus b1 square, that. So this is what the magnitude of a, magnitude of b. So how to find the cos of angle? So I'll perform the dot product, okay, divided by magnitude of a multiplied magnitude of b. And now how to find this angle? So I can write angle np dot arc cos. Arc cos basically means cos inverse, cosine inverse. So because now I have computed this cosine angle, I'll just use this cosine angle and multiply it by 180 divided by n pi, so that I convert into degrees. Okay, this is the degree conversion between the angle. If you know how to convert these radians into degrees, so I'm converting this into degrees. So every computation that I have done so far, we have explained that onto our board. Now you can clearly see we have an angle. As we have these vectors, we computed angle from those things. And now I want to plot that angle and plot everything that we have so far. And this plotting, you can just read it. It's really easy to plot the things because we have extensively went over the matplotlib. So now you see that we have this vector a, this vector a red, then we have this vector b as well. This is the vector b. Now if you see the angle between two vectors, I think this arc should be in between these two. So this is 31.33 degrees. Somehow like I sort of made this graph like look like this, but it should be the angle between a and b. Sorry for this typo. So it should be the angle between a and b. So at degree is 31.33 degrees. So did you got how I computed this angle and how I showed it in the code window as well? Can I move forward?
Yes, sir.
Nice. So again, I showed you the property of orthogonality as well. So orthogonality means if a dot b is equal to 0, then there is sure shot that these two vectors will be at a 90-degree angle. So let's do one thing. Let me show it in the code and I'll show you the visualization if they really are at 90 degree. Okay. So here I have vector 3 comma 0 and 0 comma 4. If you see these two vectors, let's compute their dot product. So let's compute their dot product because I have these vectors. I have a vector a which is equal to 3 comma 0, and then I have vector b which is equal to 0 comma 4. If I perform a dot b, that's equal to 3 multiplied by 0 is 0 plus 0 multiplied by 4 is 0. So a dot b is 0. Now if I plot them on our 2D Cartesian plane, so I should get these vectors somewhere like this. They should be at 90-degree angle. Okay, so if I plot it, let me show you the plot. So I'll plot these two vectors. So you can see that these two are orthogonal to each other because the dot product is 0 and these two are orthogonal to each other. Is the concept of orthogonality clear?
Yes, sir.
Because these are the building blocks. These things are your building blocks. Whenever you understand them really well, and if you need to watch this lecture 1-2 times, it's worth it. Because I haven't seen any lecture series, I haven't seen any book which explains the concept in this way. Because this is how I struggled myself. Because when I was reading about the algebra, I sort of cannot wrap my head around why are we doing multiplication in this format? Why are we doing such certain things? Because I lack these concepts. So when I was in my undergrad, that time I had to like read through the books. There is a good lecture series by Gilbert Strang, and then I found these things. Okay, this is how actually we should perceive these matrices and determinants. Yet I haven't used the word matrices in the whole thing because I first want to make the things clear so that I can use the matrix now. Then I'll perform the dot product. I'll perform these matrix products and things like that. But I want you to have these foundational blocks really clear. There should be no gap even because in mathematics, if there is a gap, between the concepts, then you don't understand the concepts really well. Maybe it, for example, if you're reading some others even in the computer science, if you suppose you take things for granted, they'll work somehow. But in mathematics, if you have a little bit of gap in the knowledge, and the whole thing falls down. So it's really important for you to understand these things better, and we'll slowly build on these things, and then you will feel there is no magic going into the machine learning. There is no magic that AI bots are able to chat with you. AI bots can create this and that. But whole of the thing is based on probability, linear algebra, statics, and optimizations. If you know these things well, then I'll sure shot give a guarantee to you people that you won't find these things difficult, because you know the basics really well and you know the fundamentals really well, and everything basically is just a combination of these fundamentals. Let's suppose if you want to create a good spectacle, you must have a good glass, you must have a good frame, and those things with you. If you have these raw materials really good, then you can create a really good thing. Similar goes with the study. So in the learning, if you have your fundamentals really strong, then you can build over these things quite well. That's the reason I'm sort of spending these time in these simple concepts. They might look simple, but if you do not know them, then they create a lot of problems in the future. So I hope that you will take these things seriously and you'll pay your full attention. Now I'll go to the other topic that's called as a projection of vectors. I'll go to on a topic that's called as projection of a vector. All these concepts I'll seriously use, because for example, I'll just give for this projection, there is a concept called as principal component analysis that basically uses this projection concept. So if you know this how projections are done, so it will be really easy for you to know the mathematical details of that concept. Many people I know that for sure 100% people who are doing the machine learning, so they might know this concept PCA. But how many people I fear like nearly 40 to nearly 50% do understand the mathematical detail. If they are really good at maths, so they know how this PCA works and how do we capture the variance and how do we use this projection vector and things like that. So it's really important because these concepts may look now basic, but when we'll be using them, if you forgot them at that time, it's really like sort of uh, uh, dip down hole for you. At that time you cannot understand and grasp the things. That's why I want you your utmost focus right now. So what is a projection? So by projection I mean, if I have a Cartesian plane like this, in that let's suppose I have two vectors. I have a vector, let's suppose A, then I have a vector, let's suppose B. The two vectors. So what I can do is, if I sort of put a torch onto this, so suppose I have a torch. I cannot make the torch good. That's why I'm a computer science major, not a art major. So here, if I put a torch on this, so you see that the shadow will be made like this. If I put the direct torch onto the top, you see that this A will get projected over this like this. You know the word projector. What is that doing? The projector basically is projecting something on the screen. So what I'm doing here is I am projecting this A onto B. So I'm sort of having a light torch with me. I'm putting a torch, and the shadow that is being casted of this A onto this B. This is called the projection. This is called a projection of A on B. Okay, it's written as like this: projection of A on B. This is the syntax how I will write this: projection of A onto B. Again, without going to the mathematical list, still I can prove this, but I want you to remember the formula. Here, this course is not about the proofs, but I urge you to do these proofs by yourself. If I have this projection of A onto B, this basically is equal to A dot B divided by B square, and then I'll put a dot over here. So this is the projection of A onto B. So again, I can prove this how I can just use Pythagoras theorem here and there and use the concept of dot product, and I can prove you this is the projection of these vectors. But again, take this as an exercise for you and prove these things, because otherwise if I go through all the proofs, it'll again take me a lot of time. So these things are for exercise for you, kept as exercise. I don't think these are really like important if you cannot do work without the proofs, but you should know these things. But the best thing is, if you want to internalize these formulas, the best way is that you must do the proof of these things. Prove these things for yourself so that you get convinced. So what are the things that we are doing here? The first thing, we're again doing dot product. Look how much important is dot product. So we are doing dot product. So this is the dot product. And again, then what we are doing is we are doing the normalization. This is called normalization or norm. This is called the magnitude, finding the magnitude. Because we'll write dot np norm. So we are doing the normalization. Okay. Then this is the direction, basically direction of B. There are three steps involved in projection. If you want to compute the projection, so what should I do is I should first compute the dot product of these two vectors a and b. Then I should find this normalized vector b, basically the magnitude of b and its square, magnitude of b squared, and then I should just find the direction of b. What is the direction that b is into? Okay, so that gives me the projection. And geometrically speaking, this is the projection. This point is the projection. Let's call it d, and this d is equal to projection of a onto b is dot product of a dot b, then divided by magnitude of b squared and multiplied by b. This gives the direction of the vector. So this is the thing that you want. Again, step one. Let me write in the steps. Step one: find the dot product. Okay, step 2 is normalize, and step 3 is direction. And by this is a dot b. If I want to find the projection of a onto b, so I can write a dot b first. So normalize, basically I'll find magnitude of b, then I'll square the magnitude. This basically is b1 plus b2 square and up to bn square, because you know that magnitude is under root of this. So when I'll put under root, and this will just square it out, square the terms up. The direction is just I'll put the b vector here. So this is find the direction. That's the geometrical interpretation of the projection. Let's consider an example. Let's suppose I have a vector a whose value is 3, 4. Then I have a vector b whose value is 1, 0. If I want to find the projection of a, I want to find projection of a onto b. So how I'll do it? I'll just perform the dot product. So what's the dot product? 3 multiplied by 1 is 3. That is 3, because 0 multiplied by 4 is 4. So this is, and then I'll find the magnitude of this. This is equal to 1. Okay, then I'll multiply the whole b to get the, actually basically this is the unit vector that I want. I'll divide by 1. So then I'll find the direction of this. So here I'll get the magnitude as 3, because here I want to get the magnitude. So magnitude of projection basically is just 3, and then with the direction. So if I want you to show the same thing in the coding, and we can just go so that this concept becomes clear. So here this is. So I have a vector, let's suppose 3, 4. Then I have a vector 5, 0. If I want to find the projection of a onto b, what I'll do is I'll calculate dot product first. So np dot a comma b. Then I'll find the magnitude b square. So np dot b comma b. Okay, so this is basically multiplied twice. This is similar thing that we have. Then projection basically is dot product divided by magnitude multiplied by b, that b, the vector b that we had. Okay, so now we have the projection. Now I have the vector a with me, I have the vector b with me. Now I will plot a, b, and the projection. So this is the figure. I'll plot this a, and I'll plot b, and I'll plot the projection. So when I plot this, you will get something like this. So this red vector was a vector, and this blue vector was a b vector, and this green vector, if you see it here, which is on this vector b. So here we have the projection, this in the green. So if you just draw perpendicular over, it is like you are just holding a torch perpendicular, and this is the shadow is casted basically here. That is the meaning of projection of a vector onto some other vector. Is the concept of projections clear? Is it clear?
Yes, sir.
Yes, sir.
Nice. Great. If it's clear, then we'll move on to the next concept, which is really important. Why is it important? Now we'll see at the equations of different things. We'll see equations of plane, we'll see equations of a line, we'll see equations of cubes and things. And why do we need them? Because as you saw in the previous session when we were doing explore data analysis, that time we saw that we can have a decision boundary. A line can be a decision boundary which will separate setosa flowers from non-setosa flowers. So in that sense, we need to define what a line means. So for example, I told you in the previous lecture that if we have flowers like this, let's suppose they have only two coordinates, petal length and petal width. Let's suppose this is petal length and this suppose petal width. Some flowers are like this, because they basically are everything basically is a point in some high dimensional space. If you have a data point which has 10 features, so what do you understand by that? It basically is a 10 feature vector which belongs to the 10 dimensional vector space. So here we have the two features, petal length and petal width. So they basically are the data points which belong to the two dimensional vector space. So let's suppose here I have some other points. Okay, so now you can clearly see that I can just draw a line like this. Okay, I can draw a line. This line is called as decision boundary. decision boundary. So this decision boundary clearly separates this class red, let's suppose this is class 1, and class 2. Now I mathematically want to model it. So how to basically draw this line? How should I mathematically have this line with me so that when I have this and I can just compute, okay, if I have this point, let's suppose I have a point like this. So I can directly say this point belongs to class 1 because this lies on this side of the decision boundary, this side of the line. So in order to understand concepts like this, I must understand the concept of line, how they are mathematically described. So that's why I'm going into the concept of these things, and I'm showing you how to describe these things, how to describe the geometric figures in mathematically basically. So I'll say what is a line basically. Line. So we'll start with the line. So line applies to 2D surfaces. So here you saw that we had a 2D surface, then we had petal width and petal length, and now we sort of made this line, and for these 2D things we have a line. So how, if you remember from your +1 +2 days, so you describe a line by y is equal to mx plus c, if you know this. So here we call this ms slope, and we call the c as intercept. So we call this y is one variable and x is these two are variables. So these two are variables. One is called as independent variable is x, and one is called dependent variable, and this m is called as slope, and this c is called as y intercept. So if I want to draw a line like this, yes, here it is. So if I have a line like this, okay, so this is y is equal to mx plus c. So m basically means how much steeper it is. So if this is like this, so this is a lot of steep, and this m shows the steepness, slope. So this is the steep. So this is m basically how much steep it is. This is the m. So if I want to show you c basically is this intercept. This is c. So why does it cut the y axis? That's why it's called y intercept. Okay, the y basically is the y axis, and x here is the x axis. So this is how it used to describe the line. So this is one equation. But if you want a general equation, generally we write this equation as ax plus by plus c is equal to 0. This is equivalent to y is equal to mx plus c. How you can call me? How is it equivalent? Because I can write by is equal to minus c minus ax. Okay, then I'll write y is equal to minus c by b minus a by b into x. So I can say, let's say this is some capital C, and this is some m, and I can write it x, and I can just add. So did you saw that these two equations are equivalent? But this is called as generalized equation, generalized equation of line. So here slope basically this m is equal to a divided by b minus a by b, and its intercept is basically equal to minus c by b. So now these two equations are basically equivalent. So because if I need to write this, I'll just replace these a's and b's with w's, and I'll replace these x and y's with x1 and x2. So I can write this equation of a line like this. Equation of a line can be represented like this. I'll say w1 x1, okay, plus w2 x2 plus, so w naught I'll write here. So w naught, because this c is alone, so I'll write w naught is equal to 0. So this I can call a general equation of the line. Okay, so again you can derive this y is equal to mx plus c here. So again to sort of iterate and again to sort of demonstrate to you that this really makes a line if you just fill in the values. So this basically makes a line. I want you to show this in the code so that you are convinced that this line can be represented by this. So let's go on to that. So here I have this x1. I just described this x1 as some values. I put some random values of x1. Then I have this x2. So what I did is I put mx plus c. This is x1. This is m slope here is 2, and this intercept is here 3. And then basically I'm dividing it by 4 to sort of make this equal. Here we have w naught is equal to 3, w1 is equal to 3, this 2, and w2 is equal to 4. And I want to find this y is equal to mx plus c wala equation. This is the equation that we have. And now if I plot these x1 and x2 onto a plot, so because I have a value x1, so if you want to print them, let's suppose I'll print this x1, and then I'll print this x2 as well, to show you that these basically are just values. They're nothing but values. So I'll just show you the values that we have these in x1 and x2. So this is the value of x1 and x2. So here we have a lot of values. So how we got these values? By just plotting this x1, by just using the formula of the line. So now if I want to Now what I do is, if I want to plot these values, if I want to plot these values by using the plot function, here the x coordinate is x1, y coordinate is x2. I'm using the red, and then this is the label of the equation. So I'm having w naught plus w1 x1 plus w2 x2. So here there are values are w1 is equal to 2, w naught is equal to 3. So these are the values. So now if I plot it, do you see this is the line basically? Are you convinced that the equation that I wrote is basically of the line?
Sir, screen is not.
Oh, so sorry. So what I'm saying here is, we have this x1. So we just have this np dot linspace in which we sort of have values. So now I'll compute this x2 by using the equation of the line that we have. So if you remember, the equation of line is w1 x1 plus w2 x2 plus w naught. Now I have this x and x1 which I call as independent variable. I assigned it some values. So now for the x2 I computed the values from that equation. Okay, if I would want to show you those values, so I'll just print out these values, print of x1, and again I'll just write print of x2. Okay, these basically are just bunch of values. If you see, they are bunch of values. I'll just run this. So this is basically a bunch of values. So x1 values, and these are y1 values. Now I'll plot these values. Okay, if I plot these values, so I'll just comment this code out. So if I plot these values, you'll see that we got a line. Are you convinced that this w0 plus w1 x1 plus w2 x2 is equal to 0 is basically
Sir,
the equation of
screen
line?
got shifted.
I don't know why it is shifting again. So are you convinced that this is basically the equation of line now? So how many of you are convinced that this equation which I wrote, w0 plus w1 x1 plus w2 x2 is equal to 0, is an equation of line? So because we just plotted these values, we gave x1 some values, we gave x2 values, and these x2 values are adjusted by using this equation, and what we got is basically this line out of this. So how many of you are convinced that this is the line? Just raise the hands and show me that you are convinced that this is an equation of line. Nice. Now you know this is the equation of line. Great. Okay. Oh, nice. So here, if this is an equation of line, it represents a straight line. So this was basically in our 2D. So what if we generalize this concept to 3D? So what will happen? So if I generalize this concept in 3D, the 3D equivalent, we have a line in 2D. The equivalent in 3D is basically a plane. So plane is basically just something like this. So we have planes like this. If we have 3D like this, and we can have a plane like this. In 2D we have some lines, maybe like this. Maybe we'll have a line like this. But in 3D, this is in 2D, and this is in 3D. In 3D we have planes. So in the similar fashion, we can write the equation of plane as well. So if you how you saw the line, we can similarly write the equation of plane. If you know how to write the equation in from your +1, where you read about the coordinate geometry, there we used, right, a plus, and then we had beta x plus, or let's suppose bx plus cy plus dz is equal to 0. So this was the equation of plane. Equation of plane. Okay, now I'll write in my terms. I'll just represent these x's with the x1s, and I'll write these coefficients with w's. So I can write w naught plus, then instead of this b, I'll write w1 x1 plus w2 x2 plus w3 x3. That's equal to 0. So this is the equation of a plane. Just extending from the line. If I just write w naught and this is equal to 0, because we have two coordinates here, x2 and x1. So that was the equation of line. When we added one more axis, x3 component, so it became a plane. So again, in order to demonstrate this, I have a proof for you that this basically is an equation of plane. So now we need three axes. So again, I'll just do one thing. I'll have this w0, w1, w2, w3 initialized. This is the initialization. So what I'll do, I'll compute x1, then compute x2, and these are independent variables. I've just given them some values, then computed this values. This is the value of x3. X1 and x2 have been given some independent values, and then I'm computing x3 by using the equation of plane that I just showed you. And now I'll plot this x1, x2, and x3. So if you see, I'll plot this. I am plotting this by here. So here we have these vectors. If you see, this is a plane basically. I'll explain you what is this. So maybe just hold on for a second, but just see that this basically is a plane living in three-dimensional axis. X1, X2, and X3 are the three axes, and here we have a plane which was defined by using our equation that we described just a few minutes ago. Are you convinced that this is the equation of plane? Are you convinced? This is very important that you get convinced that this is basically an equation of plane, because whole of these things, they basically depend on these things, because then we'll be writing this equation in succinct format and things like that. But I want you to get convinced that this equation is basically an equation of a plane. Okay, now we saw 2D, there is line, then we saw in 3D, it is a plane. In 4D or ND, this is called as hyperplane. This is called as hyperplane. Now we cannot imagine hyperplanes, but still the mathematics gives a power. That's why algebra and mathematics is so beautiful, because whatever we can't imagine, still we can make computations. We can sort of manipulate these things by using the mathematics, irrespective whether we are having an imagination to imagine that or not. But still we can sort of use the mathematics. So again, if I have, let's suppose, n-dimensional plane, so their axes are x1 comma x2 comma x3 till x1 till xn, sorry. So how to represent this hyperplane? I can represent it like this: w naught plus w1 x1 plus w2 x2 plus and so on plus wn xn is equal to 0. So this is the equation of an ND plane. ND plane basically means an hyperplane. This is a hyperplane. Okay, this is really important to understand. So now we'll sort of tinker with this equation to make it succinct. Okay, so here if I can write it like this: w naught, okay, plus, so this is w1 x1. Can I, you just saw dot product. Let's suppose I have vector w. I have vector w which is like this: x1, let's suppose w1, w2 and so on till wn. This is my vector w. Let's suppose I have vector x which I can write like this: x1, x2 and so on till xn. Okay, can I write it like this? I can write w transpose of x, that is equal to 0. Just look at this equation again. Look at this equation. Just I'll expand it for you guys. So here I have w naught plus. So w transpose basically makes this as a row vector. So here I'll get it like this: w1, w2 and so on till wn. And here x is again a column vector. So x1, x2 and so on till xn. So here is the dot product. So if I dot them, don't you think that I'll get this back? So that's why I wrote it like this: w naught plus w transpose x is equal to 0. This w naught basically gives where does this plane go from. If the value of w naught is 0, then this plane goes from origin. If plane passes through origin, if plane passes through origin, okay, then we can write w transpose x is equal to 0. So this is the equation of plane. Equation of plane passing through origin. I just wrote it in a succinct way. This w transpose is basically this w vector, okay, and then this axis, they are the axes that we have in the ND plane. And if it is passing through origin, I can omit this w naught. So I can just write the equation of plane in a succinct way. That's the power of algebra. You saw we condensed a huge equation into just two simple words. Now you sort of understand this. If you read the research papers, there you will frequently see w transpose x plus something like this. Now you understand this basically is x vector. This is nothing but a vector. This x is nothing but a vector. So they are performing the dot product, and this is, if is written like this, this is an equation of a plane. Is this clear? If this is clear, you have sort of unlocked another dimension to read machine learning and things.
Yes, sir.
Nice. So this is how I wrote the equation of the plane in this format. So just remember this. So this w vector, this basically is a normal vector. As you know that this w transpose x, it is a dot product. Again, this is a dot product. If dot product is equal to 0, so what did I told you? That they follow the property of orthogonality. That means this vector w and x, they are orthogonal to each other. So they are perpendicular to each other. That's the beauty. I told you that if dot product equals 0, then theta, angle between these two vectors, because w is a vector and basically this x is a vector. So this means that this w is orthogonal to all the axes that we have. So we cannot imagine this basically. Let's suppose we have n axes and each axis is perpendicular to each other. Then we have a vector W. Let's suppose if we have this plane in 3D, we have a plane like this. Let's suppose this is the plane. So these points lie x1, x2, x3. These are points which lie on this. So what I'm saying, W is like this. So W is a vector which is perpendicular to all these points. So it is perpendicular to all these points that lie on that plane. If there is a plane on which the points lie, W is basically a vector which lie on that, which is perpendicular to all these points. That is what I have demonstrated here. So if you see this, if you see it on the coding window, I have this normal vector, W vector. So it is W1, W2, and W3. When I'm plotting it, this basically is normal to this plane. Maybe it does not look normal to this, but exactly this is normal. So if I had this plane sort of which was visually looking like a straight plane, then you will see that this is perpendicular line. So this plane basically is like this. So this plane is basically like this, and here we have a the normal vector, W vector. It's called normal vector to this. So do you saw the connection between this dot product and how we sort of arrange these things? And do you have the intuition now? So that's the first thing I want you, because if you are really good at these fundamentals, if you really good understand these things by heart, and if you understand these things by all your soul, then machine learning becomes really easy for you. Then you won't find magic in these things. You'll find that these are just the fundamental building blocks are stuck here and there, and we found something, and we got. And let me show you some things, like how do we make these spam filters and things like that. If we have data like this, so which lies in 3D, so some data will be like this, for example, and then we will have some data points like this. So you will just form a plane like this, which just separates out these things. So you will say a plane. Oh, sorry. I hope it's visible because I'm seeing it on here. Is it visible?
It's not visible.
Okay, so what I was saying is, if there are points lying on one side of the plane and there are points lying on the other side of the plane, so you can easily draw a plane by using the simple algebraic equation, by using these w's and x's. So you can sort of make the filters. So if you want to make a binary classification task, your job is to find this plane. If the data is linearly separable, the whole point of that algorithm is basically to give me this plane, so that I can find I can find the plane, and I can separate the data. Whatever lies on the left hand side of data is one side, and whatever lies on the right hand side is one line. That's called as, these are called as half spaces. Half spaces. Because you know that even if you have any dimension of the things and you form a hyperplane in that, so it divides the space into two things. That's called as positive half space, positive half space, and that is called as negative half space. Okay, so that's that's the thing that these planes do. Hyperplanes, they just have these are basically linear, and what they do is they'll just convert these planes, they'll just divide your system into two half spaces. One is called as positive half space, and there is called as negative half space. Okay, so if you have now you have this plane, W transpose x is equal to 0. If you see that, if you have any point, let's suppose we have a point x1, if you write W transpose x1, it was greater than 0, that means it lied on this side of the plane. This is called as positive half space. So if it was greater than 0, so it belongs to positive half space. So if we had a point x1, again it was W transpose x1 was less than 0, that means the point was on the negative half space. If W transpose x1 was equal to 0, it lies on the plane. The point lies on the plane. Because now you saw that if we have some sort of data points that separate across our vector space like this. So here we have these green points, then we have these red points, if you see. So now we just dropped a plane in here. This is our plane that we have. This is the plane. And it is sort of dividing the space into positive half space and negative half space. So if there is a point which gives us the value W transpose x less than 0, it belongs to the negative half space. If there is a point x1 which gives W transpose x is equal greater than 0, then it belongs to the positive half space. Let's suppose these were setosa flowers and these were non-setosa flowers. Now you just have to find this W vector. You have to find this W vector. And you will just perform the multiplication of this W vector with the point. For example, let's suppose we have this x1 as sepal length, petal length, and sepal weight. These were the 3 points that we have. If we found this W transpose W1, W2, and W3, that was our W, vector W. So what you'll do is, you'll perform W transpose, and let's suppose this is the point vector, and you will just perform the dot product of this x1. If it is greater than 0, then you will say this is setosa flower, and if it is less than 0, you will say it is non-setosa. That is the classification that we did by using the planes. Is the concept of planes clear? Hyperplanes clear? So we wrote the equation. What is the equation of hyperplane? Again, to reiterate, W transpose X is equal to 0. And this is the equation of the plane, hyperplane passing through the origin. And this W is called the normal vector. Can I move ahead? Is this clear?
Yes, sir.
So you understand the things?
Yes, sir.
Nice. Hmm. We have some time left. Let's go again. Now I want to find the distance of a point from a plane. As we saw, we found the distance from the origin, then distance between 2 points. What I'll see is I'll find the distance between a point and a plane. So the topic is distance of a point, basically a vector from a plane. Okay, so that even can be we can have a line, and if we have in 2D, that will be a line. So if it's line like this, so if I have a point on P, and this line may be y is equal to mx plus c, and I want to find this distance basically. And in 2D, I'll have something. This is the 3D plane. Let's suppose we'll have a plane like this. Let's suppose we have a point in here, and we want to find the distance of this point P onto this plane. And similarly, in the hyperplane, we can do the similar things that we have. Okay. So again, the derivation of this point, I don't want you to derive these things, but what I want you to do is I'll just write the formula, and then maybe you will sort of try to prove it yourselves. So the formula, the formula that I'll give here is, so there was a LaTeX problem in here. Let me just see where is the formula. So I'll just give the formula. Otherwise, I need to derive the formula that I want to do here, because I want to leave all of these things for you so that you can give the exercises. I have written a lot of notes for these things. So here I. So what is the formula? What is the distance d? Let's suppose this is d. Let's suppose this is d again. So in the hyperplane, that can be d. So what is this d equal to? So this distance basically d. Let's call it d. So the formula of d is equal w naught plus w1 x naught plus w2 y naught plus w2 z naught divided by under root of w1 square plus w2 square plus w3 square. So as you know, we have a vector w. We have this vector w, which is w1, w2, and w3. I'm just showing it in the 3D, so you can extend it later on. So I have this point P, which is equal to x naught, comma y naught, comma z naught. So if I want to find the distance of this point P onto this w, so what is the distance like this? So this point is x naught, comma y naught, comma z naught. Okay, so I want to find this distance d. So this is the plane for which I have defined this w. So this w is equal w1, w2, and w3. Okay, so how I can formulate distance? Basically, I can just write this w naught, w1 x naught plus w2. As you can see, this again is a dot product. So how I can write it? It's like this. So d is equal to, so directly saying, I'll say w naught, okay, plus, so this w can be written as w transpose, then this point whatever it is, I can write it as p dot p divided by, this basically is norm of w, that is the norm of w, the magnitude of the point w. This is the magnitude of w. If it is passing through the origin, if the plane is passing through origin, then I don't need this w want as well. So I can write this d is equal to w transpose dot p divided by the magnitude of w. This is again, this formula is an exercise. Again, this is not hard to prove exercise. So I have given you multiple things to prove for yourself so that you get convinced about these things. So now this distance, this w can be even d is equal to, we can have this w as w1, w2, and so on till wn. So we have an nd plane, hyperplane. Then this point can lie in the n-dimensional plane. So we have x1, x2, and so on till xn. So what is the equation? So we'll just write w transpose dot p. We'll perform dot product of these two. Then we'll write the norm of w, basically the magnitude of w. So in order to sort of just expand it, it'll be w1 x1 plus w2 x2, and so on till wn xn divided by under root of w1 square plus w2 square, and so on wn square. is the concept of distance if you want to find a distance of a point or a vector from a plane. Is it clear? Is it clear?
Yes, sir.
Again, just for your convincing that you get convinced that these things do exist, so I'll just make a plane and a point and I'll compute the distance and show you the distance. Let's go to the coding window. So here what I have done is I have again formed a plane. This is my plane. Okay, so this is my point. So here I have a point. So now what I'll do is I have this point P. So this point P is there, and then I have this plane. So this is the point x1, x0, y0, 0. This is our point. This is the our normal vector w0, w1, w3 is a normal vector, and from this vector I can basically create a plane. I have created a plane by using this. So these basically define our plane, whatever the equation that we have been using. Now I compute the distance. Distance is equal to w1 x0 plus w2 y0 plus w3 z0 plus this w0. I'm assuming it's passing from origin, so I can write this w0 as 0, and then I'm np dot square root w1 square, w2 square, and w3 square. So that's what I'm doing here. So now I'm plotting these things. I want to compute the distance. So if you see, this is the plane. Okay, then we have a point, this p point, and now the distance is 3.27. So this is how the formula basically is that we discussed I think few minutes ago. Now this is clear. If this is the plane has been defined by using the equation of plane, and then we have a point which lies in 3 dimension, and if we want to compute the distance, so there is a formula of distance that I have given you, and you can just compute it and you can see the visualization. Is this concept clear? Is it clear?
Yes,
Is
sir.
it clear? Nice. So is the concept of half space is clear as well. So hyperplane, what do they do? So I'll again write half spaces. They sort of divide the space into two things. One is called a positive half space, and one is called as negative half space. So if you perform the dot product of these points, so the points for the which W transpose X is greater than 0, they belong to positive half space, and W transpose X, if it is less than 0, they belong to negative half space, and if W transpose X is equal to 0, they are on the plane. Now you don't need to visualize. Now you can just perform mathematical computations. You can just say set of the nonce. You can just make a decision boundary based on that. Okay, so what are the applications? So I said in the classification, I just showed the application of classification. There is something called a convex hull in comprehension geometry. So you can also have applications there. In optimizations, we have applications of this plane. Okay, let's again draw a line for these for the points. Again, I want to sort of convince you that we can do classification with these things. So let me just go to the code and let me show you there. So here what I have done is, so if you see in here, so I have just have a class 1 and class 2. So there are random points, some random points that I have drawn from class 1 and class 2. So again I am having a line, I'm trying to fit a line onto these points. So then I'm plotting these things. So if you see, so it sort of separated these red points clearly, and some we have some misclassification because this was done randomly. But you saw that we can do the classification based on this line only. Similar with the plane as well. So you can just have a hyperplane or a 2D plane. Then you can sort of divide the whole space into two half space. One is called as positive half space, and this is called as negative half space. And one class may belong to positive half space, and another class may belong to negative half space. Is the concept of these hyperplanes, planes, and how they are used in classification clear? Can I move ahead with this?
Yes, sir.
Nice. Now there are some other figures that we use usually in the classification as a decision boundary. So first thing is I'll say circle. So now it will hardly take us another 10-15 minutes, and we'll wrap up the basics of this algebra, and so that you got the visualizations. And from the next lecture onwards, we'll go into a lot of mathematical details that we'll be using. But now I want you to sort of have watch this lecture again, so that you sort of feel that you know these concepts really well. So this circle looks like this. If there's a circle and this circle, usually it looks like this. So this is the origin in 2D plane. I'll have this circle. So what if this, let's suppose this is not an origin, this circle, let's suppose the center of circle lies somewhere here, and this coordinate of this center is h comma k. Okay, so the equation of circle is x minus h whole square plus y minus k whole square is equal to r square. Let's suppose the circle radius of circle is r. This is r radius. Okay, so this is the general equation of circle. Let's suppose if it passes through the origin, so what I can do is I can just write x square plus y square is equal to r square. So this is the equation of circle passing through origin, whose center is at origin. Circle's center is at origin. Okay, so this is the equation of the circle, and this is in 2D. So in 3D, we call a circle a sphere. Okay. Similarly, we can have the same things. First, I would like to show you the circle. If I want to show you the circle, how to draw the circle, again in the code, you can use the matplotlib. So just having these classes, so you have this cluster. It can just bring in the cluster within itself. So here it's random data, but still you can see that we dropped a circle, so we can fit in whole of the blue points into our circle. So this is how circles can be used as decision boundaries. And sometimes the circles are really useful in, if we have data and we are sort of shifting the data to high dimension. I don't think you will understand it right now, but just keep that in mind that sometimes we use these circular boundaries to sort of classify the data into separate classes. So this is the circle that I wanted to show you. And the equation of the circle that we used is this equation that I showed you on here. So this is the equation of the circle. It is passing through origin, and here this is the general equation of the circle. So if this circle is plotted in 3D, if we have a 3D like this, we have x, we have y, and we have z, it basically becomes a sphere. Okay, it becomes a sphere, and you can just have again x square plus y square plus z square is equal to r square. So now we have the sphere. So let's suppose its radius is r again. So we'll say x square plus y square plus z square is r square. So this is the equation of sphere whose center is at origin. So you can also use spheres to do this. Then we have something called as ellipses. So we have these circles, then in 3D we have spheres. Then we can say we have hyperspheres in ND. So in ND we have hyperspheres. So what is the equation? Equation is x1 square plus x2 square plus and so on till xn square is equal to r square. So this is the equation of hyperspheres, because we can just imagine on to these spheres and these circles and these circles. That's why I'm writing this equation. I'm visualizing in 2D and 3D, but for the ND I'm writing these equations. Then we can have these ellipses as well. So the equation of ellipse as well. So we have ellipses. So ellipse is something like this. So if you see it, like it's like this. Just stretch the circle. If you stretch it, so this we call it as a minor axis. So we call this as minor axis, and this is called as major axis. Major axis. Let's suppose this is A and this is B. This is A and let's suppose this is B. So what is the equation of this? So basically we'll write x by A square plus y by B square is equal. It has some radius and it has, let's suppose, r by is equal to r square or something. Okay, so you can see the equation of the ellipse. So I don't exactly remember the equation, but you can just find the equation of this. So this is in 2D. So in 3D this will be called as an ellipsoid. So ellipsoid. So just in 3D you will have as another z axis over here. So in ND we'll call them, hyperellipsoid. Again, you'll just extend the equation. Whatever the equation is there, you will just extend these things. Then we can also plot rectangles. Okay, then we can plot cubes and cuboids like this, because rectangle is in 2D. In 3D we have these cubes and cuboids. In ND we call them as hypercubes. Hypercubes. Okay, I just want to show you all of these things in the coding window so that you get some sort of visualizations for this. I have written the code for that by using the same equations. So just going back to the coding window to show you these things. So here first I have these plotted these ellipses, and then I have plotted these sphere circles and everything. If you see it here, so here I have this sphere. If you see it, sorry, if you see it here, we have a sphere, we have an ellipse, we have an ellipsoid. This is in 3D. Okay, circle basically is in 2D. That I showed you circle previously. So this is the circle. So from the circle we get sphere in 3D. So in 2D we have an ellipse, in 3D we have an ellipsoid. This is an ellipsoid. Then we have this rectangle in 2D. Then we can make this cuboid or the cube. We can just plot these things and hypercubes. We can just imagine, we can just visualize only 2D and 3D figure. That's what I'm showing in here. But you can also sort of visualize the things that not visualize, basically write it mathematically, those things which you cannot imagine, but you can sort of manipulate and describe these things by using the linear algebra. I'll sort of end this session over here, and I'll take questions because there's a lot of things that you have seen today. I want to take the feedback from you. Was it good, and have you had some good concept, learned some concepts regarding this? If you have questions, I'll stop here for a few seconds and I'll stop the recording. Okay, I think there are no questions. Maybe I'll just stop the recording.